All right. 4.07, perimeter area and composite figures. Pause the video and see if you can identify which postulate and or theorem makes the triangles congruent. Take a moment and answer this warm-up. All right, so we should have said angle, angle, side. You can see we have two angles and a non-included side for both triangles. So the corresponding angles that are congruent and the non-included side pair that are congruent means angle, angle, side is the answer to this question. Our objectives today are going to be to determine perimeters of rectangles using coordinates and triangles using coordinates, areas of rectangles and triangles using coordinates, and perimeters and of polygons using coordinates, along with area of composite figures using coordinates. We'll start by reviewing what perimeter means and practicing problems, and reviewing area and practicing problems, and then practicing solving composite figures. So to start off with perimeter, the perimeter is the distance around a plane figure. So the perimeter of a polygon is the sum of the lengths of the sides. And the example below demonstrates how you might write out what the perimeter is. It is the sum of A plus B plus C plus D plus E. So it's the sum of A, B, C, D, and E. And remember that right there is a pentagon because it has 5 sides and it's a polygon, so it is a pentagon. Now, as far as equations are concerned, certain shapes have basic equations that we utilize to describe the perimeter of the figure, right? So we're talking about the shapes of like squares and rectangles, circle, triangle, parallelogram, and trapezoid. So in this particular case, it's always about adding up all the sides of the figure, or in the case of the circle, we can see that it is the circumference, which is sometimes what that's referred to, 2 pi r. So having said that, it might be helpful to keep a reference of that, screenshotting that particular formula page, because it can be used in future questions and problems. So in this case, however, what I want you to do is pause the video and see if you can correctly identify the correct perimeter of the figure. So this is just another pentagon, and the perimeter is again the sum of all the sides of the actual figure. So if you take 7.1 and you add 3.2 to 2.8 to 5.8 to 3.2, we have our 5 sides, and we add all of that up together, we get 22.1. So the answer that you should have selected was the bottom option. Keep in mind that perimeter is a linear measurement. That's an important point to bring up. Linear measurements also are measured using the same units as each individual side length. So that means the perimeter is 22.1 centimeters, and it's because it's also a linear measurement. So pause the video and see if you can come up with the perimeter of this figure. So this one's even easier. It's just a triangle, and we look at the perimeter of the triangle as the sum of all the sides. So 3 plus 4 plus 5 is going to be 12 centimeters. So we have 12 centimeters for our answer. So that third option is the answer to the question. Now area is where you take the number of square units contained in an interior of the figure, and those square units in particular are unit measurements, which means that are unit squares. Unit squares are squares that have lengths of 1 and then whatever the unit actually is, if it's meters or centimeters or inches. So that square is a 1 by 1, and when you break up the figure in that particular case, you can come up with the area of the whole figure by combining all of the areas of each of those unit squares together, however many there actually are. Okay, So if both the base and the height are in the same units, the little boxes that make up the area will always be 1 by 1. That's what makes it a square unit as a result. That's what square unit actually means. How many of those 1 by 1s can we actually create inside of an actual figure? That's what we're looking at here. And remember, this is two-dimensional, not one-dimensional, right? So this is two-dimensional. What two-dimensional basically means in this context is it's not a linear measurement. That's why we have to square the units in that context. So if we look at rectangles and triangles, for example, for a rectangle, we simply have to take the area of the base, or the area equals, rather, the base length times the height. And interestingly enough, if you take a rectangle, like you can see right here, and you cut it in half, you're literally taking the area of a rectangle and cutting it in half. So that's why we take 1/2 the base times the height when we're trying to find the area of a triangle, because that is half of the rectangle that it otherwise would be, right? So if this were a parallelogram, for example, if I were to extend this out, even make it like a parallelogram, exact same triangle in every way, it's just inverted. Again, same height, this would be the same base, then the area of the whole figure would just be base times height. So cutting it in half allows you to see why the area of the triangle works the way that it does. So the altitude of a triangle is going to be perpendicular to the base length of the opposite side of the vertex. So in the diagram that you saw moments ago, we had a triangle whose altitude was drawn. The altitude is represented by the actual segment that comes from the vertex here and the side opposite the vertex, which is this side length right here. So those two things are needed, and the relationship that we want you to take away from that is that it's perpendicular. All right. Now, the altitude is the actual segment itself, right? That's what this thing is. The measure of the altitude is actually what we refer to as the height, right? So the height of the triangle. So the height is the actual measure of the altitude, or the measurement, or length of the altitude. Actually, length is probably a better word because you're dealing with a segment. So the length of the altitude. That's why we use H rather than A. So any side of a triangle can actually be a base. Right? Any side of a triangle can be the base. So all triangles have 3 altitudes, no matter what, and it can lie inside or on or outside the triangle. And that's dependent in many ways on the type of triangle that you actually have. So if you look at these examples here, this illustrates the different types that you can have, and the red line represents the altitude, and the blue lines represent the bases of those triangles. So for example, if your triangle over here is what we refer to as an obtuse triangle, that just means that one of the angles, let's say this angle, is actually greater than 90 degrees, less than 180, and the altitude lies outside. If it is a right triangle, which we recognize right away, then it lies actually right here on, right? It's on the triangle. And then if it's an acute triangle, every angle in the triangle is less than 90, then the altitude itself is inside of the triangle instead. So the height changes its location based on, or rather the segment that represents the altitude, again, that's what the altitude is going to be different depending on the type of triangle that you're working with. And it also depends on, for right triangles, how you've oriented it. But no matter what, in any one of those cases, the base and the height are still going to be what you need to calculate the area. It's still going to be half base times height. So let's take a look at this example here, and I'm going to have you pause and see if you can come up with the area of the rectangle, and the formulas are provided for both rectangle and triangle above as well. See if you can come up with the area of the rectangle that we have. Hopefully you said 162 square feet, right? So we know that the area of a rectangle is the base times the height. The base could be 18 if you wanted to call the base 18. The height could end up being 9. I'll show you that when you take 18 times 9, or if you want to use parentheses, that's fine too, you end up with 162. It doesn't matter whether you said 18 times 9 or 19 times 8, you're still going to get 162. No matter what, you still end up with the same exact area, right? So that's square units, right? Square feet. So that means there's 162 little squares in there that have dimensions in feet 1 by 1. Okay, and there's 162 of them based off of the dimensions of that rectangle. So pause the video and see if you can come up with the area of this particular triangle. So here we should have selected the middle option, 30 square feet, as our answer. There's lots of ways you can do this. The formula is probably the best way, right? You have the base times the height divided by 2. And so the base, you can consider the base as 12 and the height as 5 if you wanted to. And you can divide by 2. You can multiply the 12 and the 5 to get 60, and you can divide that by 2. And you end up with 30, right? 30 square feet. So that's going to end up being our answer here. There are other ways to simplify this answer once we've plugged everything in. There's other ways to approach finding the area using the rectangle formula, but you'll have to, at one point or another, end up dividing it by 2 to get the final answer. So I'm showing you just how you can use the formula to get your resulting answer. Now, a composite figure, some people pronounce it composite or composite. I say composite, all right? You can say it either way because it's correct. So the composite figure area is going to be a combination of regular shapes that are recognizable combined together. So it's the area of a number of polygons that combine to create the overall shape. And you can add or subtract the areas based off whatever you prefer, what might be easiest. You have some examples here as well where you have an arrow and you have another shape that might look like a building or a house, or it could be something, anything. Could be just a general shape. It is, however, a composite figure. So the tip here that we prescribe to you is that you really ought to split up or break up the figure into shapes you can easily find the areas of. Or the areas for. Okay, so in other words, you just want to break them up into shapes that are easily recognizable and combine those through either addition or subtraction depending on whatever is your preference. So let's take a look at an example where we can break this up into different components here. So the first thing I want you to know is that the figure right away is really made up of a quadrilateral and a triangle. In this case, the rectangle that you see in the bottom half or bottom portion of the figure, and then you have the triangle in blue, which is represented as sitting on top of this. So you have two separate areas. Sometimes I like to refer to it as area 1 and area 2. So area 1 is the triangle area, and the base of the triangle, if we break it up into the two pieces, I guess kind of nicely enough, I'll just place them over the actual areas that they are. We have a 4 centimeter base and an 8 centimeter height, and you're adding that to a rectangle that just so happens to be a 4 by 9, right? So the length here is 4, the length here is 9, and you're getting the actual areas of those two figures, which you see here and here, right? So this is going to be area 1, this is going to be area 2. So they're using the formulas for the area of a triangle and a rectangle to figure out the total area of the figure. It isn't the only way to do it, however, but it is certainly one of the ways that it could have been done. So another way that it could have been done, and I'll do this on the side over here, is if you were to have, let's say, completed the figure. Completing the figure means making it recognizable as one singular shape. So I've made it into an entire rectangle, and so I might consider the area of the full rectangle, let's call it area total. This one would be a rectangle, which would be a 4 by 17. 4 times 17 is going to end up being 68, and that would be centimeters squared. Now that represents the total area of the entire figure. This piece right here, however, is not actually a part of the real figure. It is a triangle, and that triangle, again, this triangle here has a height of 8 and a base of 4. So the area of the triangle, right, which is going to be the same thing as area 1, is going to be 8 times 4 divided by 2. That's going to get me 16 centimeters squared. So then the area that I'm interested in, which I'm going to highlight in green, is only this region right here, this entire shape. So this is an example in my approach where I need to subtract the area of the triangle, which again, that area is in orange right here, from the total area of the figure, right? So the area that I care about is going to be, the area of the composite figure. I'll just call it A. I should just take the area of the total, and I subtract the area of the triangle from that. So I get 68 minus the 16, and that gets me 52 square centimeters. So that is another way that the area could have been found, demonstrating subtraction as opposed to addition. So there's more than one way to find the area of a composite figure. It's up to you to decide how you want to go about doing that. I would say that no particular approach here is better than the other. It's simply that they both provide the right area. So looking at this example, I would encourage you to try different approaches even to the one that I do. But if you'd like, the way that this is set up is to help break it down for you, so you have a strategy to use to help you figure out how to go about doing it. For example, I'm already noticing this triangle sitting on top of what otherwise is a very innocent looking rectangle. So the two shapes that I have are a triangle and a rectangle. So what I'm doing in the back of my mind is I'm already thinking about recognizable shapes whose area formulas I already know. Area of a rectangle, which I'm calling that, is just the base times the height. And then the area of a triangle is going to represent the base times the height, but divided by 2. So I'm already aware of what I need to utilize, right? In fact, I should have written that over here. Area of the triangle is going to represent, in this case, the base times the height divided by 2. The area of the rectangle is going to equal base times the height. So it says plug the numbers into the area equations. So we have to identify what those numbers actually are. Well, in this particular case, we need to make sure we know what this length is. We know the total length is 7, and part of the length at the top here is 3. So what plus 3 gets you 7? Well, 7 minus 3 is equal to 4. So that particular length is 4 feet. So the base of the triangle is going to be 4, and the height of the triangle is going to be 3. So you can kind of plug 3 in there, and we just have to divide that in half. So that tells me the area of the triangle is going to be 6. The area of the rectangle has a base of 7 and a height of 9. So we have 7 times 9. So the area of the rectangle is going to be 63, right? So right now we know the area of the triangle is 6 square feet. The area of the rectangle is 63 square feet. So what do? Well, we need to combine them. Combine them isn't necessarily always the best word or phrase to use. Sometimes it's helpful to describe exactly what we're going to do, right? Which means that we need to add them. We need to add them because that's the important bit there. So the area total is going to equal the area of the triangle plus the area of the rectangle. So that's going to be 6 plus the 63, which makes 69 square feet. So that's going to end up being the total area of the composite figure that we have. That probably is one of the easiest ways to solve that problem. I would give the tip as well that it's better if you can, when you're trying to break it up into recognizable shapes, try to go about the approach of doing so with the minimal number of shapes possible. We only had 2 shapes here to work with, right? If you're breaking it up into a whole bunch of different shapes, you're also opening yourself up for the possibility of making a lot more computational mistakes because you're including a lot more in there. So we have one more here. Again, look at the strategy. We have a 2 inch by 2 inch square, which is cut out of what otherwise was a right triangle, and it gives us the base length and the height of the triangle, and so we want to find the remaining triangle area. So this is the perfect example of where now something is actually missing from what otherwise was the original figure. So the 2 shapes that we can identify here are a triangle and a square, as opposed to a triangle and a rectangle. So those are the 2 shapes that we recognize. And the area of a triangle, as we know, area A sub t is base times height divided by 2. The area of a square, okay, remember with the area of a square, it's just the side length squared. Okay, so sometimes we use S to describe side length, right? So just remember that S means side length. And the reason it's just that is because all 4 sides of a square are the same. We want to plug in our information. So for the area of the triangle, our base is 10, our height is 6, and we're going to divide that by 2. For the square, we simply have a side length of 2, and we are going to square that as well. Okay, so we're squaring the side length there. So here we end up with an area of the triangle being 30 square inches, and the area of the actual square itself is going to be 4 square inches. So we need to subtract in this case rather than add, right? We need to subtract, and the reason we need to subtract is because the area total that we have available in green is the difference between the area of the triangle and the area of the square. It's missing that little tiny square piece. So 30 minus the 4 is 26 square inches. So that's going to be the area of that composite figure. Alrighty, so that's going to be the lesson 4.07 for our exit ticket on this particular date.